Okay, let me start sharing my screen. I have already started recording this session. We'll start the session, others will join later or may go through the recording. Welcome everyone to the Tom class. This is our third problem solving session. So far we have studied the problems on the first topic. First session was analysis on the analysis of linear mechanism. Then the second session was mainly on the gears and gear trains. And now we will start with the flywheels in the third session. Okay, if time permits, we'll also discuss the problems on the governors as well. Okay, so write down heading flywheels. Before we jump into these problems, for the first question, like what is the purpose of the flywheel? What is the purpose of the flywheel? Like when so we know the flywheel is something which will act as a reservoir for the energy, correct? It will act as a reservoir for the energy, so it will store the energy and it will give the energy whenever it is required. And the main purpose of it is why we want to do so is to minimize the cyclic fluctuations. Okay, we wanted to minimize the cyclic fluctuations, and for that purpose we use flywheel. Flywheels, so I would say it is acts as a reservoir of energy. And minimize the cyclic fluctuations in the engine speed. Minimizes cyclic fluctuations in the engine speed. Okay, so this is the main job of the flywheel, and whenever, let's say, a flywheel initial rotation is, let's say, maximum kinetic energy is the main formula from this topic we have to understand is maximum kinetic energy is half of I omega 1 square, and minimum kinetic energy is half of I omega 2 square. Okay, then the delta omega, sorry, the delta E, change in the kinetic energy, is equal to kinetic energy maximum minus minimum kinetic energy, and that will be equal to half of I omega 1 square minus omega 2 square, correct? So this much amount of energy is stored in the flywheel, you can say, right? And then which we can utilize half of I omega 1 square minus omega 2 square is omega 1 plus omega 2, and this is omega 1 minus omega 2. Okay, omega 1 plus omega 2, and this other one is omega 1 minus omega 2. Okay, and then we basically say that half of I, not I, half, let's say this part, 1 divided by 2 I'll do here. Omega 1 plus omega 2 divided by 2 is how much? Omega, that is the average RPM, sorry, average radian per second, or you can say average angular velocity. And then delta omega is omega 1 minus omega 2. Now if I multiply by omega and divide by omega, I can further write it as I omega square into delta omega by omega. This is your delta E. Okay. You can also write it as I omega square CS. Okay. This is your delta E. Delta E can further be written as 2 into half of I omega square into CS. What is this I omega square? It is the energy corresponding to the average omega. So this implies delta E by E is equal to 2CS. Okay, or delta E is equal to 2ECS also we can say delta E 2E. Yes. Okay. So this is the final answer you can say. So, and all the problems in the when we study the numericals will be associated. You can solve them by using this formulation. Okay, if this formulation is clear, you can solve any problem. Okay, the derivation is very easy. It's not, no need to remember anything. You can easily derive things there. Okay, so let's start with some questions. Some of the theoretical questions, some of the numerical questions. Majority of the numerical questions we will solve. Okay. First question: the radius of gyration of a solid disk. So I'm taking the problems which we have not studied before. Okay, in the previous session when we studied the flywheel, we also solved some questions. So I'm not repeating them. These are the new ones. The radius of gyration of solid disk by flywheel of diameter d is. Okay, so options are d by under root 8, d by root 2, and under root 3 by 2d. Okay, so by using this, we can solve the problem. um, Look at the options. So you know radius of gyration k is for disk type flywheel, radius of gyration is r by root 2. Please give me 1 minute. Is wrong with the presentation. You can, yeah, you can in the meantime proceed with the solution. Okay, because of some reason I cannot switch to the presentation mode, but yeah, let's continue. Let me try. Yes, I think it worked now. Yes, so we can say that for solid this type flywheel, k is equal to r by root 2. Okay, so k is equal to d by 2 root 2, we can say. So it means d by under root of 8. Okay, so this is something we should know. That radius of gyration for the solid disk type flywheel is r by root 2. Okay, one of the similar question I have for rim type flywheel. Let me go to the next slide and give that one. If the rotating mass of a rim type flywheel is distributed on another rim type is distributed on another rim type flywheel whose mean radius is half uh, whose mean radius is half mean radius of the former. Okay, we'll stop. Then energy stored in the latter at the same speed will be. Then the energy stored in the latter at same speed will be. Okay. Options 4 times same as first one, 1/4 of first one, and half of first one. Okay, yeah, this one you try to solve this. Energy stored is what? Energy stored is delta E is equal to I omega square Cs. Okay, this is one of the formula. So, and this is one more point for the rim type flywheel. I is equal to mk square and k is equal to r, so it is mr square. Okay, k is equal to r, so it is like same thing. Previously we said k is equal to r by root 2 for disk type flywheel, and here you remember k is equal to r for the rim type flywheel. Okay, so remember this difference, and depending on what kind of question comes, you have to apply the value of r accordingly. Okay, apply the value of k accordingly. Okay, um, so now tell me the uh, tell me the answer here. The answer in this question is option C, 1/4 of the first one, because you are reducing, you're making half of the radius, so half of 1/2 square is 1/4, so that's why answer is 1/4. Okay, because it's directly proportional to the radius square, and if you are reducing the radius by half, then it is half a square is 1/4. Okay, so here 1/4 is the answer. Next question. Yes. In a system with a flywheel, the coefficient of fluctuation of the speed the coefficient of fluctuation of speed is 0.04, full stop. the fluctuation of energy is 1 kilonewton meter. Okay, the mean energy of the flywheel is mean energy of the flywheel is, okay, 25 kilonewton, 12.5 kilonewton, um, okay, kilonewton meter, sorry, 440 kilonewton meter, 4 kilonewton meter. Okay, so 25, 12.5, 40, and 4 kilonewton meter. These are the options. Try to solve this one. The mean energy of the flywheel is, again, formula you already know, that delta E in terms of mean energy is 2 ECS. 2 ECS. So we know the value of how much delta E? Fluctuation of the energy is 1 kilonewton meter. That is equal to 2 into E into CS. CS is coefficient of fluctuation speed, that is 0.04. Okay, that is delta omega by omega. Okay, CS is equal to coefficient of fluctuation of the speed, and that is 0.04. Okay, and um, there is also a concept called as coefficient of fluctuation of energy, that is delta E by E. So remember, whenever coefficient of fluctuation of energy is given, that is delta E by E. And whenever the coefficient of fluctuation of speed is given, that is delta omega by omega. Okay. So here they have mentioned just the fluctuation of energy, not the coefficient of fluctuation of energy. So that's why we considered only delta E, okay, and delta is equal to 1. Okay, so the formula, let me explain the formula here. Delta E is equal to 2 ECS. Sometimes they'll say, or delta E by E is equal to 2 CS. Delta E by E is CE, coefficient of fluctuation of the energy, is equal to 2 times coefficient of fluctuation of the speed. Okay, this is also something you should know. So from this, let's say the value of E will be 12.5 kilonewton meter. Okay, so option B is correct in this case. Quickly write it down. Okay, the next question is theoretical. Match the list A and B. So I have the list 1, and I have the list 2. List 1 says flywheel. Flywheels, governors, shock absorbers. Okay, and last one is vibration control. Okay, list 2. Speed control, energy control, vibration control, fuel control. Okay, so this is the list. The purpose of flywheel is What purpose of governor? Governor is for controlling the speed, I would say. Okay. Shack, then R, I would say 2. Um, so yeah, I think yeah, you can just ignore this uh, vibration control because I think this is repeating. Yes. So flywheels, you can say that. Um, yeah, again, it will control the speed, right? But yeah, you can also say it as vibration control. Okay, to avoid the vibrations. Governor is to maintain the speed, and um, yeah, just a minute. Sorry. Mm, Flywheel is energy control. Okay. Governor is controlling the fuel. Okay, and shock absorber is the vibration control. So speed control is not the aim here. Flywheel will control the energy. It will store the energy and then give it whenever required, right? That is what we have studied. Governor will control the fuel input, and then that fuel input will be used for the um, um, then we can go further. Sorry, governor has to be a fuel control, and then shock absorber is the vibration control. Okay, so this is the right choice, I would say. P2, Q4, and R3. Okay. Next question. In an engine, the flywheel is replaced by another one, another one having double the moment of inertia, having double the moment of inertia. Its coefficient of fluctuation of speed will be its coefficient of fluctuation of speed will be, and the options are like reduced by 25%, reduced by 3%, remains same. The last ones will be doubled. Okay, try to solve this one. The answer is reduced by 50%. Okay. Let me give the solution. In an engine, the flywheel is replaced by the another flywheel having double the moment of inertia. So coefficient of fluctuation of speed is what? Uh, Delta E is equal to I omega square CS, right? So CS will be delta E divided by I omega square. So um, the flywheel is replaced. So this is for the first flywheel. For the second flywheel, double the moment of inertia. So CS will be delta E divided by 2I omega square. Okay. Its coefficient of fluctuation of speed will be so this is CS1 and CS2. You can clearly see that will be reduced by half, right? It is 1 by 2 times the first equation. So that's why it is reduced by half. Okay. Okay. Next question. A simplified turning moment diagram of a two-stroke IC engine is shown below. A simplified turning moment diagram of a two-stroke IC engine is shown below. The torque developed by the engine in Newton meter is torque developed by the engine in Newton meter is okay. So it is minus 2 pi and 2 pi. So we have theta and yes, this is the turning moment diagram. I would say it is Tn 0. Okay. This is in Newton meter. Options are given to you as 5, 6, 4, 8. Okay. 5, 6, 4, 8. So the net work done per cycle is equal to 10 pi minus 2 pi, that is equal to 8 pi. Okay, and what they are okay, the expectation here is torque here. So the mean torque here will be 8 pi, and this is over the 2 pi range, okay, or 2 pi theta degree, theta angle. So divided by theta if you do, work done is equal to t into theta. So we are just subtracting the areas, and then mean torque, if you calculate, if you divide the work done with a theta, you will end up with the torque. And so this 8 pi, we got the net work done over the theta of 2 pi. So that's why I'm divided with 2 pi. So 4 Newton meter is the answer. Hence option C is correct in this case. Okay. Okay, I have one question which is with a linked data. Okay, so a little bit bigger question. So we have two questions based on a common data. Yeah, I'll explain you in the next slide. So let me go to the next slide, write down this question. Couple of questions with the linked data I have. The first one we'll discuss now. Uh, the turning moment diagram of a four-stroke single cylinder IC engine. The turning moment diagram of four-stroke single cylinder IC engine. Okay, can be approximated as rectangles. Can be approximated as rectangles in each of the stroke with the areas of 2 centimeters square. Okay, with the areas of 2 centimeters square. Okay, I would say negative. During suction stroke, during suction stroke, 4 centimeters square, negative. During compression stroke, (57 centimeters square), positive. During power stroke, um, suction stroke, 4 centimeters square during the suction stroke, 57 centimeters square positive. During power stroke, okay, and 3 centimeters square negative during exhaust stroke. Okay, during exhaust stroke. Full stop. It is drawn to a scale of 1 centimeter is equal to pi radian, and 1 centimeter is equal to 100 Newton meter. It runs at a mean speed of 600 RPM. The first question is the constant load torque the engine can handle is the constant load torque the engine can handle is. Okay, and the second question. um, so the first question is the answer is in kilonewton meter. You have to, so you can start working on it. In the meantime, I'll write the second question. The moment of inertia of flywheel. Okay, the moment of inertia of the flywheel required to limit the fluctuation of the speed. speed within plus or minus 1% of the mean speed is. Okay, answer is kilojoule kg kg meter square. Okay, yeah, start solving these questions. I'll give you a minute of time, think on it, and start solving it. Okay, the turning moment diagram of a 4-stroke single-cylinder IC engine can be approximated as each of the stroke with areas they are given. Okay. So now the first one is a constant load torque. So let me draw this diagram first. So all three are negative, -2, -4, then +57, and then -3. Okay, so this is, let's say, the 0 scale, -2 is a suction, then the -4, then third one is 57, and then we have -3. Okay, -2, -4, -3, and 57. And let's say this is the mean value. Okay, so this is the given diagram. Now, what they are asking is the constant torque. So yeah, before we jump into the torque calculations, what is the work done? So first you have to calculate the work done and then divide with the 4 pi. You will, because this is your pi, this is your 2 pi, this is your 3 pi, and this is 4 pi. And when we divide with the theta, you will get the torque. Correct? So mean torque. So work done per cycle is equal to -2 -4 plus 57 -3, which will be 48 centimeter square. That is 4800 pi. Okay, 4800 pi. Mean torque is equal to 4800 pi divided by 4 pi. So which is 1200 Newton meter. Okay, which is 1.2 kilonewton meter. Okay, 1.2 kilonewton meter. So this is the answer for the first question, 1.2. Now, second question, the moment of inertia of the flywheel to limit the fluctuation of the speed within plus or minus 1%. Okay. So plus or minus 1% means plus side 1%, minus side 1%. So it is 2% in total, right? So CS will be 0.02. So I have given you the hint. CS is 0.02. And yes, with this hint, you can proceed and tell me the answer quickly. That so the delta E is, we can say, the fluctuation in the energy is equal to I omega square CS. Okay, I is something which we have to calculate. We calculated the value of omega is yeah, we have to calculate again because they have given us the. Okay, just a minute. Check what else they have given. Yeah, the mean speed they have given 600 RPM. So corresponding to the 600 RPM, 2 pi into 600 divided by 60 whole square, you can calculate. And then you have CS. Okay. Um, CS is um, um, CS is 0.02. So now I think, yeah, with this you can solve the problem. Okay, I'll give you a minute of time. Okay. Let me do the solution. The value of delta E is first we have to calculate. Delta E is, I would say, fluctuation of energy, and that will be area above the mean torque line. That will be area above the mean torque line. Above the mean torque line. And that will be how much? 5700 pi is the maximum. Okay, and the mean is 1200 pi. Okay, we just calculated. It will be like 4500 pi. Okay, so I have given you the enough hint. With this hint, you can solve the question. So the answer will be 4500 pi is equal to I omega square CS, and that will be I into 2 pi into 600 divided by 60 whole square into 0.02. This implies I is equal to 179 kg meter square. Okay, 179 is the final answer. I'll write it here. Okay, so yeah, I'll wait for a minute. You can just quickly write it down and then we'll proceed towards the next question. Okay, next question is here. Four-stroke IC engine develops. Four-stroke IC engine develops 60 kilowatt with a mean torque of the mean torque of 600 Newton meter. Stop. The fluctuation of energy is assumed to be fluctuation of energy is assumed to be 50% of the energy developed per cycle. Okay, energy developed per cycle. The moment of inertia of the flywheel to keep the total fluctuation of the speed within 2% of the mean speed is, okay, the moment of inertia keep the total fluctuation, keep the speed fluctuation within 2% of mean speed is, okay, kg meter square is the answer, right? The answer will be in terms of kg meter square. Try to solve this one. Mm, okay. Okay, let me help you out with the solution here. So the question here is about the value of I. Okay, so P is given as 62 kilowatt. Then T mean is equal to 600 Newton meter. Energy developed per cycle. Energy developed per cycle is equal to T mean into 4 pi, which is 600 into 4 pi. That is 7539.8 joule. Okay, 7539.8 joule. Okay, delta E is 50%. Just a minute. much delta E will be? 50% of 7539, right? That is what they said. Okay, that will be, you will get 1200 pi. That will be 1200 pi you will get, because you can clearly see 4 pi divided by 2 will be 2 pi, so 600 multiplied by 2 is 1200 pi. Okay, so in a simplified way I'm writing, not in the complete answer. Okay, so this is something you can consider. And then we have delta E, which is equal to I omega square CS. So this implies 1200 pi is equal to I into 100 square into 0.02. This implies I is equal to 18.85 kg meter square. Okay, so 18.85 is the final answer in this case. Okay. Okay. So next question. Let me check for another question. Okay, little bit different type of question. Yeah, A prime mover develops torque T is equal to 1000 plus 500 sine theta Newton meter. Okay, look at the formula. Okay, different one. Where theta is a crank angle, where theta is crank angle, and rho is a constant load. Rho is a constant load. Okay. The mean speed of the engine is 100 radian per second. The mean speed of the engine is 100 radian per second. And the allowable fluctuation of speed is the allowable fluctuation of speed is 2% on either side of the mean speed. On either side of mean speed. The moment of inertia of the flywheel, required is okay, moment of inertia of the flywheel required is. So start solving this. They are asking the value of I. The answer is in again kg meter square. Little bit different question than what we have studied. Here torque they have given as an equation 1000 plus 500 sine of theta. So the mean torque is 1 upon 2 pi integration 0 to 2 pi t d theta. Okay, remember this formula. Okay, or write it down. Um, so 0 to 2 pi t sine of theta. So it will be 1 upon 2 pi 0 to 2 pi t is 100 plus 500 sine theta d theta. Okay, which will be 100 Newton meter. Okay, so we got the mean torque. Delta torque is equal to change in torque at that instead of at any instead of time will be t minus t mean is equal to 1000 plus 500 sine theta minus 1000, which will be 500 sine theta. Okay, so this is my delta t. What we can say, the change is zero. Okay, the change in torque will be zero when delta t is zero. So that is delta t is equal to zero. This means 500 sin theta is zero, and this implies the value of theta has to be 0 degrees or 180 degrees or 360 degrees in the range of 0 to pi, you can say. Okay, so this is the first thing. So what we can consider is delta E is equal to integration 0 to pi 500 sin theta, and that is equal to minus 500 because sin theta integration minus cos theta cos 180 minus cos 0. So what is cos 180? Cos 180 is minus 1 and cos 0 is 1. So minus 1 becomes minus 2 multiplied with the minus 500. It will become 1000 Newton meter. So this will be your delta E because it is above uh, the, or let's say the delta E is not the overall work, it is delta E. Okay, so delta E is I omega square CS. This implies 1000 has to be equal to I. Omega is 100 square 0.04. You can clearly see they have written clearly here the mean speed of the engine is 100 radian per second and an allowable fluctuation is 2% on either side, either positive or negative. So CS is 0.04. Positive side 0.04, 0.02, negative side 0.02, so total 0.04. Okay. So if you calculate it, you will get the value of I equal to 2.5 kg meter square. Okay, 2.5 kg meter square. So this was something different. Let me go to another slide. Next question. A double acting steam engine develops 6 kilowatt or 6 kilowatt at TRPM. The fluctuation of the energy is fluctuation of energies 6% of energy developed per cycle. Okay, energy developed per cycle. Full stop. It has a flywheel moment of inertia. It has a flywheel moment of inertia. 100 kg meter square. Full stop. The maximum variation in speed is here they are asking you the how much is the maximum variation in the speed. Delta omega is something they are asking. Okay, but not delta omega, delta n I would say, because delta omega then it is in the radian per second, and as it is delta omega, uh, as it is in the RPM, it is delta E. Okay. So let me give you the solution here. 10, 60 RPM, omega, 2 pi radian per second. Power is equal to 6 kilowatt, and that is equal to 2 pi and T mean torque divided by 60. So this implies T mean is what? 6,000. 6,000. So N is 60. Okay, so this will get cancelled. 6,000 divided by 2 pi, I would say. Okay, Newton meter. So and T mean into theta is equal to work done per cycle. So 6,000 divided by 2 pi multiplied by 2 pi is equal to 6,000 Newton meter is the work done per cycle. Okay, so you got the work done per cycle. Okay, I'll write it down till this point, then I'll go to the next slide and explain you the other points. Okay, I'll go to the next slide. Yes, so here delta E is equal to 6. How much is the delta E? 6% of the energy developed per cycle, fluctuation of the energy, right? It has, yeah, so 6 by 100 of 6,000, which is 360 joules, okay? And delta E, is half of I. mm, um, Omega, delta omega, right? So yes, 360 is equal to half of I is how much? 100. Omega is 2 pi, or not half of I omega, just I omega delta omega. So half will go I omega delta omega. So from this you will calculate the delta omega, which is 0.573 radian per second. Okay, then delta n is equal to 6. Yeah, omega is equal to 2 pi by 60, so delta n will be equal to 60 into delta omega by 2 pi, which will be 60 into 0.573 divided by 2 pi, which will be 5.47 RPM. Okay, so the 5.47 is the final answer in this case. Okay, so this is how we can solve it. Next question. A flywheel has to rotate at 100 radian per second. Its permissible hoop stress is 320 megapascal, and its density is 8,000 kg per meter cube. Okay, 8,000 kg per meter cube. The maximum possible mean radius of the flywheel is the maximum possible mean radius for the flywheel is so and so centimeter. Okay, in centimeters you have to find the answer. Um, so yes, it's permissible hoop stresses. So rho c, I would say. Sorry, sigma c is that is hoop stress. Centrifugal is rho v square. Okay, so that is rho r square omega square, we can say. So the value of r is rho c by, sorry, sigma c by rho omega square. Okay, under root. So your sigma c, that is permissible hoop stress, is 320 megapascal, so 10 raised to the power 6. Density is 8,000 multiplied by omega is 100 radian per second square. You will end up with a 2 meter, which means 200 centimeter. Okay, 200 is the final answer in this case. Okay, this is something, a new formula. If you are not aware of this, please write it down. I'll go to the next slide. We have another question. A flywheel in a system is shifted to another shaft. A flywheel in a system is shifted to another shaft which rotates at double the speed of the other one. Speed of either one. Full stop. The coefficient of fluctuation of speed compared to the previous one is the coefficient of fluctuation of speed. Very easy question. Compared to the previous one is. Okay, the options are remain same, reduced by half, will be doubled, will reduce to 1 by 4. So these kind of options are there. So a flywheel in a system is shifted to the another shaft which rotates at a double speed of the other one. The coefficient of fluctuation of speed compared to the previous one is, so you know, delta E is I omega square CS. Okay, so this is equation number 1. Delta E 1, delta E2 will be I. If the shaft speed is doubled, so 2 omega square CS, what will happen? It will be 4 times, and then the ratio will become 1/4, right? The coefficient of fluctuation of speed compared to the previous is sorry, coefficient of fluctuation of the speed they are asking. So CS1 and CS2. So from this we can say CS1 is inversely proportional to the omega. CS1 is inversely proportional to the omega 1. So CS2 is inversely proportional to the 4 times omega 1, right? So because 2 is omega 1 square, sorry, 4 times omega 1 square. So it will be, I would say, that is reduced by 1/4. Okay, reduced by 1/4 is the answer. Okay, next question. A punching machine punches 600 holes per hour and driven by an electric motor. Driven by an electric motor. Okay, driven by an electric motor. Supplying uniform power. Supplying uniform power. Stop. The actual punching takes 2 seconds and requires 2 seconds and requires 12 kilojoule of energy. Stuff. The fluctuation of energy, fluctuation of energy that is to be controlled by the flywheel is. That is to be controlled by a flywheel. It's okay. The options are like 7.5 kilojoule, 8 kilojoule, 9 kilojoule, and 6 kilojoule. Okay, try to solve this one. Okay, if you look into the chapters apart from the flywheel, the topics are governors, okay, balancing, then cams, and gyroscope. Okay, we have studied small cams is a very small topic, and we have studied already a lot of questions on it. Um, even the gyroscope, we have studied the problems. So maybe in the next session, we will focus more on the balancing and governors. These two topics. If yeah, today also, if time permits, I'll take some questions of the governors. Okay. Um, but yeah, maybe let's solve one or two more questions on the flywheels, and then we can go back to the um, uh, one or two questions on the flywheels, and then we can go to the governors. Okay. So major, I think we'll focus more on the governors and the balancing. Okay. Uh, yes. Coming back to this question, this is about the fluctuation in the energy. So let me explain you the procedure here. So yeah, this is the torque and this is the time. So a punching machine punches 600 holes per hour and is driven by an electric motor supplying uniform power. The actual punch-in takes place 2 seconds and it requires 12 kilojoule of energy. Okay. So 600 holes per hour, it means 10 holes per minute. Okay. It means 6 holes per or 6 seconds per hole. Okay. And out of this 6 seconds, 2 seconds is actual punching. Okay. So I would say 2 seconds, let's say maybe 4 to 6 is the actual punching. And this is the average, you can say. Okay. And they requires 12 kilojoule of energy. The fluctuation of the delta is something they're asking. Okay. So power delivered, power of the motor to be delivered is 12 kilojoule. Okay, it requires 12 kilojoule of energy. So the given data says that power of the motor delivered um, or to deliver, okay, to be delivered 12 kilojoule of energy during 6 seconds is 12 kilojoule. oh sorry, 2 kilojoule, 2 into 6 is 12, right? So I would say delta E is equal to 2 into 4. Okay, so yeah, so this is your 2 kilojoule, and yeah, so this is, we can say, the energy stored, right? This part, 2 into 4 seconds, it will store the energy, 8 kilojoule, and then it will use it in the 4 to 6 seconds. Okay, hence option B is correct, which is 8 kilojoule. Okay, okay, we'll take one more question on the flywheels, and um, okay, one or two more questions on the flywheel, and then we'll move towards the governors. Let's take another question. A flywheel fitted to a steam engine has a mass of 800 kg. Its radius of gyration is radius of gyration is 360 millimeter. The starting torque of the engine is 580 Newton meter. The starting torque of the engine is 580 Newton meter, and maybe assumed constant. Okay, so find the kinetic energy of the flywheel after find the kinetic energy of the flywheel after 12 seconds. Kilojoules. Um, yeah, start solving this question. Angular acceleration alpha is equal to T by I, which is T by mk square, pi AT by 800 to 0.36 square. So you will get 5.59 radian per second square. Okay, so this is the value of alpha. Torque is equal to I alpha, so alpha is equal to T by I, and I is equal to mk square, where mass is your 800 right, kg, and radius of gyration is 360 millimeter, which is 0.36 meter. We also know V is equal to U plus AT, so omega 2 can be written as omega 1 plus alpha T. So omega 1, which is 0, okay, initial speed. Alpha is 5.59 to T is 12. Okay, because after 12 seconds they are asking 67.08 radian per second. Okay, 67.08 radian per second. Kinetic energy is equal to half of I omega square, half of mk square omega square will be half of 800 into 0.36 square into 67.08 square, 233.27 kilojoule. 233.27 is the answer. Okay, one last question. Okay, I'll wait for a minute and then proceed to the next slide. Okay, an engine fitted with a flywheel of mass moment of inertia 50 kg meter square has the torque Vs. Okay, torque versus crank angle diagram shown below. Crank angle diagram shown below. The maximum acceleration of the flywheel is the maximum acceleration of the flywheel is. Okay. Okay, so it is 12 is minus 2 pi 2 pi radians, and this is in this is the torque. Okay, which is the kilonewton meter, and that is theta in the radian. Okay, options are given to you. 100 meter per second square, 120 meter per second square, 140 meter per second square. Option D is none. Okay, try to solve this one. Last problem from the flywheels topic. So an engine fitted with a flywheel of a mass moment of inertia, I is given to you. Okay, that is 50. Okay, they have given you the stuff already. So I would say the mean torque into 2 pi will be equal to minus 2 into pi plus 12 into pi, correct? Which is 10 pi. So Tm is equal to, I would say, 5 kilonewton meter. So mean torque is 5 kilonewton meter. Okay, this is something we have calculated. Now, I'll go to the next slide. Maximum delta T is how much? 7 into 10 raised to the power 3. That is equal to I alpha. So what is maximum delta T? Okay, um, so you can, let's say, take a difference directly. 12 minus mean is, sorry, 12 minus 5, which is mean, is 7. Okay, so 7 to 10 raised to the power 3 is equal to I alpha. So I would say 7 to 10 raised to the power 3 is equal to 50 alpha. So this implies alpha is equal to 140 meter per second square. Okay, 150 meter per second square. Okay, I hope things are clear to you. I'll go back, quickly write it down, and then we'll move towards the next topic, governors. Okay, next slide. Okay, yes, let's proceed towards the next slide now, and we will start the discussion about the governors. Write down heading governors. Okay, let me just quickly open the slides of this topic where we studied it in detail. Yes, I'll share my screen. Okay, give me 1 minute. Yes, so this is the theoretical part which we have studied in the governor. Let's quickly I'll explain what we have studied in this. We understood the purpose of the governor is to maintain the speed of the engine um, by controlling the variation, okay, or controlling this supply of the fuel, okay. And the purpose of this is like why we are doing this, because as there is a change in the load, okay, when there is a change in the load, speed of the engine will change, okay, but we want to maintain the speed even though the load is changing, and that is achieved by means of the governor, okay. And this is how it is different from the flywheels. Flywheels were used during each revolution. We have some cyclic fluctuation because we have only one power stroke where power is produced, and at the other strokes like suction, compression, and exhaust stroke, power is used, right? So you can clearly see in a single cycle, suction, compression, power, and exhaust, we have the cyclic variation, okay, cyclic fluctuation, and these cyclic fluctuation we can avoid by using the flywheel, okay. And but the governor is something different. Governor is over the number of revolutions, like whenever we change the load, whenever load on the um, engine is changed, then you can call it as a load variation, uh, which is over the number of revolutions, and at that point we can say governor is used to maintain the speed of the engine. Okay, and after that we studied there are two different types of governors, centrifugal governor and the inertia governor. And yes, the main focus was the centrifugal governor, where we studied the concept where we studied four types of governors, that is Watt governor, Porter governor, Proel governor, and the Hartnell governor. And some of the concepts of related to the governor also we have studied, which are like sensitiveness of the governor, which is sensitivity, hunting, isochronism, stability, and the effort. Okay, so this is what is something we have studied. Okay, then yeah, one important thing I would like to highlight here is, as far as all the governors are concerned, you should know the formula, which is this H. How H is related to the N. Okay, so H is equal to 895 by N square. Um, okay, this is something you should know. Then similarly, you should, for Porter governor, how the formula will be different. 895 by h, n square is equal to 895 by h, fine. But we have some additional terms. Okay, 2mg plus capital Mg plus or minus f into 1 plus k divided by 2mg. If k is equal to 1, that is tan of beta by theta. That is arm lengths are same. Then this is the case you have to use formula. You can reduce it like this. Then if friction force is 0, this is how it will look like. And if both friction force is 0 as well as k is equal to 1, then the formula is the very simplified one. N square is equal to 895 h m plus m by m. Okay? Mostly this is something they will ask. Okay. Next question, or sorry, next is parole governor. In parole governor, these are the formulas. Again, remember, this is the original formula. A by E term is there only. So it's the same as that of the Porter, only A by E is there. Okay, in all the cases, you have to put A by E, A by E as it is. Okay. And then Hartnell governor, the formulation is a bit different here. You should remember this formula, these two formulas, that is F1 into A is equal to half of mg plus fs1 plus f into b. Okay, and so on. Okay. Yeah, I think that's all. Other are the basic concepts which we have already discussed about. Okay, and then this is the effort of the governor formula. So this is the overview, just to give you um, just to revise what we have studied in this topic. Okay, I think now we can go towards the problems. Um, Give me a minute. We'll mainly focus on the numerical questions here. Um, let's take a question. Just a minute. Okay, the controlling force in a spring control governor is 1500 Newton. When the radius of the rotation of the balls is when the radius of the rotation of the balls is 200 millimeter, and 887.5 Newton. Full stop. When it is 130 mm, when it is 130 mm, not full stop here. When it is 130 mm, full stop. Okay. So the spring control force, sorry, the controlling force in a spring control governor is 1500 Newton when the radius of the rotation of the balls is 200 millimeter. Okay. And 887.5 when it is 130 millimeter. Okay. It's like this. The mass of each ball is 8 kg. The mass of each ball is 8 kgs. By changing the initial tension, the governor behaves as isochronous governor. By changing the initial tension, the governor behaves as isochronous governor. The change in the tension and the isochronous speed are change in tension and isochronous speed are. Okay. Yes. So there is a linear relationship. Okay. So they have clearly given the controlling force of a spring control governor is 1500. So when the radius of rotation, so F is equal to AR plus B, if you assume it, then you can say if when it is 1500, it was 200A plus B. Okay. And when it is 887.5, the radius, corresponding radius was 130A plus B. Okay, you can just consider these two as simultaneous equations and solve it. This is from the first line of the problem. Okay, you can figure it out and then just you can subtract, or like, yeah, subtract. What will happen is B will get cancelled and you will get the value of it. So 200 minus 130 is 70A, and this is 1500 plus 887.5, which is, yeah, since we are no, sorry, it's negative 612.5. Okay, so this implies A will be 87.5. You will get, and then if you put it into any of the equation, um, you will get B is equal to minus 2500. Um, okay, let me check it once again. Not 7A, 70A, sorry. Let me correct this. So it will be 8.75. Okay, and then B will be, yeah, minus 250 Newton. Okay, please do this correction. Okay, and then, but what is isochronous governor? We studied this. The isochronous governor is the one where B is 0, right? So far, write it down till this point, and then I'll proceed to the next slide. we know for isochronous governor, B is equal to 0. So F is equal to mr omega square, which is E times R plus 0, correct? Um, then you can say E has to be equal to m omega square in this case. So E is 8.75 Newton per millimeter. Okay, into 1000 is equal to 8 omega square. And this implies how much? And omega is equal to 2 pi n by 60. So the answer which they are asking is, yeah, the options are in terms of RPM and the Newton. So basically, yes, the 250 Newton is correct. Okay. Mm, the change in the tension and the isochronous speed. So change in the tension here is this, but the isochronous speed is they want in RPM. So you have to simplify this 8.75 multiply by 1000, 8750 divided by it. So I think you'll get omega is equal to 1093.75. Um, which is 33.07 radian per second. So multiply by 60 divided by 2 divided by pi. I think you'll get close to, sorry, n is equal to omega into 60 divided by 2 pi, which is 33.07 into 60 divided by 2 pi, which will be 315.8. So it's close to 316. Okay, 316 is the final answer. Okay. Okay, let's take one last question as we are very close to the end of the session. In a Porter governor, each arm is 200 millimeter long and is pivoted at the axis of the rotation. The mass of each ball is 5 kg. Mass of each ball is Okay. The mass of each ball is 5 kg, and load on sleeve is 30 kg when it is at a radial distance. When it is at a radial distance of 140 millimeter. What is the controlling force? What is the controlling force? Um, Options: 336 Newton, 356 Newton, 345 Newton, 350 Newton. Okay, these are the options. So, yes, the controlling force in the Porter governor is R by H, mg plus mg plus or minus F by 2. Okay, here also we have studied some different notation also. That's also fine. A by B or something. Okay. 1 plus K. So in this case, they have given K is equal to 1. That is the equal arms. Each arm is same length, and coefficient of friction is 0. Okay. Then with this assumption, you know this formula will change to R by H, M plus M, G. Okay. So this is the formula. Then yeah, write down it as equation number 1. H is under root of L square minus R square, which is under root of 0.2 square minus 0.14 square, which is 0.143 meter. F is 336.14 Newton. Okay, we can calculate directly, or let me write it. F is equal to R by H to M plus M into G. You just put the values here, and yeah, you'll get the answer as 336.14 Newton. Okay. Yeah, I think we are already at the end of the session. Let's end our discussion here. In the next session, we will also discuss uh, about some more topics. Okay, some more questions from the governors, then from the balancing. Okay, mainly these two topics. Yeah, and we will conclude the problems. Okay, so the major topics which we are already studied. If the as far as the problems are concerned, most probably the problems will be from the uh, analysis of the planar mechanisms. Okay, which includes mechanisms and machine velocity, acceleration, forces, and all. And the second important aspect is a gear and gear trains, and the third important aspect is a flywheel. Okay, and then later on the other stuff comes. But yes, we will also discuss on it in the next session. Okay, so that's all for today. Thank you all for joining this session, and let's continue on weekend. Thank you all. Bye.